My name is Jesper Løve Hindrik, and I'm currently a postdoc at the section for Cognitive Systems, Technical University of Denmark, which is in Denmark, as Rasmus mentioned. And then I do a thing on the side that's called GrowMath, together with Rasmus and Beatrice, where we do Perfect 2 on GCMS data broadly. The section for Cognitive System has a lot of people, but the Tensor group is kind of where I'm at, and these are some of my colleagues that I thought you should know of. Okay, my research is very much in Bayesian statistics, tensor methods, matrix decomposition, and then towards a lot of different life science applications, especially within analytical chemistry. So right now, maybe NMR or nuclear magnetic resonance imaging. So these things up here and 2D NMR, but also other types of spectroscopy or neuroimaging and stuff. So quite a broad range of applications. But to kind of take a step back is to say what is it even that we are solving? So we all kind of know linear regression. We have some outcome Y, we have some data in X, we have some parameters that we don't know. And then we have some model errors. And we can kind of write this as a vector with vector responses and a matrix of covariates, and then of course similarly a matrix of parameters. And we can really write this as a matrix form in having matrix output. And this is all very interesting when you have some outcomes Y. Usually we don't in matrix and tensor factorizations. So if we start with matrix factorizations, we kind of say, well, this X, that's the only thing we know. We have no Y. So we try to decompose X using some sort of meaningful constraints into two matrices, A and B, plus some noise of this modeling. And that can kind of be graphically represented as some big data matrix X that we decompose into a tall and a flat matrix, and then each column is a component. And this is not at all new. And I think the most popular one is principal components analysis, where we have that these matrices are orthogonal, and then they have a diagonal scaling matrix. The next most popular, I would say, is non-negative matrix factorization, NMF, or in the chemometrics literature known as multivariate curve resolution, which essentially splits the data into A and B, but subject to that these matrices should only have non-negative signals. So that makes a lot of sense if you do any kind of analytical chemistry where you have positive or non-negative concentrations or non-negative spectra. For instance, there are other types here, 3, but there are many more. Another thing I work on is, well, what if we look into this noise assumption? So most methods will look at what is called homoscedastic noise. So that's just the same amount of noise at every pixel, at every value of your X matrix. It's the same noise. So I've been exploring both a heteroscedastic noise. So that would say that the different, well, basically it's a different error structure. So now maybe your features, or if you look at spectral information, then maybe there are some areas of the spectra that is more noisy due to how the instrumentation behaves. Or it might be that you have outlying samples that are simply outliers because they have a huge error source. Mm-hmm. And then you do time and spatial dependence if your problem is fit to it. And all of this is kind of linear methods. And you can, of course, make it nonlinear either through kind of a generalized linear transformation. So this is what generalized linear models does. That we kind of map our output into a linear space, or we can kind of put activation functions on our latent patterns or the interaction of them. So this is also something that I'm looking into, but mainly really staying with the linear constraints or the bilinearity or trilinearity. So Mostly I like to work with the tensors. Sometimes I have to work with only matrices, but I like mostly working with tensors. So here we can kind of take a set of matrices, stack them in a third dimension, and these are called kind of the modes of the matrix. So we have first mode, the second mode, and then the third mode is the depth. And similar to matrix decomposition, we can decompose this into now 3 sets of matrices, A, B, and C. Now, the choice of how you decompose depends on your goal and also on the problem. So the most common ones are the Cantor Parapack. So Rasmus has especially used this a lot for fluorescence emission excitation matrices, and shown that this is really the physical model for that. So here you have some data matrices, and then you have your components. The first component here, the first column here is multiplied to the second column here the first column here is multiplied to the first row here and to the first row in C, and that outer product then gives one of your chemical compounds. And then if you have a mixture, you will have many columns. The second widely used one is Tucker. That's more for its compression matrix. It does kind of the same. It has A, B, and C here, but instead of only allowing the first component to interact across mode, it now allows any interactions. And that is quite powerful for compression. And if you can impose some structure on G, then it can also be very useful for interpretation. But that's one. So those are the two main ones. You can also have matrices of different length. So one method for doing that is called Parapack 2, which I'll only briefly touch about. But I just wanted to let you know that there are matrices of uneven size. So what is Bayesian tensor decomposition or probabilistic tensor decomposition are kind of used interchangeably also by me. So if we look at just how do we do least squares tensor decomposition or maximum likelihood tensor decomposition versus Bayesian tensor decomposition, it all starts with you have some data, you have some modeling here specified as a Tucker model. So you have the core array, you have your factor matrices, you have your noise, and then you can kind of see, well, the model is the Tucker model. So you could put substitute M for all of this. Now you want to estimate these model parameters, and what most people do is doing least squares estimation, or equivalently a maximum likelihood estimation under a Gaussian distribution. And this gives what's called a point estimate. So that is that there's like a single true value of the spectra, or a single true value of the parameters. Is kind of what you're assuming when you do least squares or maximum likelihood. So Bayesian inference tries to model the parameters as random variables, and if you have a random variable, it will have some distribution, and we call the distribution of the parameters the estimated distribution of the parameters, we call that for the posterior distribution. So if you had a Gaussian distribution, you would have a mean and a variance, so you get both kind of an idea of where the parameters most probably are and how spread out they are. So the kind of very high level approach looks like this. Maximum likelihood, you take your data, you subtract your model, then you measure the error, and then you try to minimize this error, possibly subject to some constraints on the core matrix and the factor matrices. It's very similar what you do in Bayesian statistics. You specify these prior distributions on your parameters theta, and here theta is just the set of your parameters. So your random variables, it's the set of random variables. That would be the proper way to call it, which is your core array, your factor matrices, and now in this simple model, the noise precision. So the noise precision is just the inverse of the variance, but for deriving Bayesian models, it's often nice that you write in noise precision rather than noise variance. It's a small detail. So you have to specify these prior distributions, which can be thought of a little bit as kind of constraints on your G and A. And then you have to specify your likelihood, which is your loss function. So in maximum likelihood here, we would have the same loss function, but without this tau. So now we have a normal distribution that says each value in our X array has some mean given by how we model it. And then there's some noise on that element as well. And then to find the optimal parameters, we have to solve this equation. So this expression here is called the posterior distribution. So it's the distribution of all our random variables given our data. So in principle, it seems very, very easy and doable. And kind of, if I have to be critical of others in my own work, it's kind of that if you have really nice data, so if you have lots of samples and you have a high signal to noise, then I would just stick with doing maximum likelihood because it's generally easier to implement, and in that scenario you're not gonna see a big difference going to a Bayesian statistics. I think that's kind of important to say. So you really have to be in an area where you either don't have many samples or you don't have a lot of nice signals. Or what Bayesian inference also does is that it kind of characterizes the uncertainty. So that's what this posterior distributions, amongst other things, does. So some of the work I've done has resulted in this probabilistic tensor decomposition toolbox, which is free to use and it's available here online. And that is described through a set of papers, mainly 1, 2, and 3. So for the CPD and Tucker and kind of the general framework behind probabilistic tensor decomposition, go to paper 1. Like if you only have to read one of these papers, spend time reading paper 1. The tensor train decomposition, which is another decomposition, and a block train decomposition, which are also another decomposition that I didn't mention before. And then we've also done some work on probabilistic perfect too, but there are some things that are not as easy and nice in that. So that's at least for now not in the toolbox. But there is code available at the associated paper, and that is also free to use. Okay, so what do you mean when I say parameter estimation, posterior distribution? So if we just take a very simple example, we just say now we have some data and we want to estimate just a single variable. Like now data is just a scalar value. Then we have some model likelihood, kind of what is the probability of X given that data has some specific value. And then we have these roughly 3 ways of estimating it. So we can do maximum likelihood estimation, and that is sort of the same as least squares. It's exactly the same as least squares if you choose a normal distribution as the likelihood. But if you use other likelihoods, then it's not the same as least squares. But in the tensor world, it's mostly the same as least squares. We can do maximum a posteriori, which also gives a point estimate, but it gives a point estimate in this posterior distribution. So you still have a random variable, you still have a distribution, and you specify a Bayesian model, but you only get like a point estimate out. And then you can do the full posterior distribution. So it gets the entire distribution of the random variable. And that is in Bayesian inference, you specify the priors, you find the posterior distribution as the likelihood times the prior, giving this P of X. And P of X is the probability of observing the data. And that is really kind of where all the trouble comes, because this P of X is the integral sum over every possible parameter choice. So as long as, or as soon as you go towards even slightly big or complicated models, you cannot calculate the integral. It becomes intractable. So you cannot get the true posterior distribution. And we want this because if we have this single univariate parameter theta centered at 0, there are kind of, there should be an A, B, and a C. Sorry for that. There are 3 scenarios, A, B, and C. So if we are here and we know, okay, theta has 0 value and like a pretty strict confidence interval, or a pretty or it doesn't have a lot of uncertainty, then we are quite certain that the data really is zero. If it has a lot of uncertainty, then it might as well be -1 or 1. And if it has infinite uncertainty, then you actually you have no idea where you are on the line. You might as well have picked -2 or -5,000. So we're really interested in having the model have this idea of uncertainty and distributions in it. Yes. So this key here is kind of what we are trying to solve, and we can do that with approximate inference. So base rule is this nice formula, and then the issue is always this one. Always this one. So there are many ways of kind of approximate or doing this. The two most common ways are based on what's called Markov chain Monte Carlo sampling or variational Bayesian inference, and they have their benefits and downsides. So sampling, we say, well, this integral cannot estimate every possible parameter of choice, but we can draw some samples, and then we can take some of those to kind of get close to what it should be. So that would be an approximation of it plus some error. And we do the choice to do this is you initialize your parameters or random variables at some value, and then you iteratively kind of update these estimates based on the parameter values and the data. So it's really, really similar to an ALS algorithm. One thing that's super nice is that this is guaranteed to at infinity. If you run it forever, it's going to be at the true posterior distribution. So it's actually going to hit the right variables. It's going to hit the right characterization of the uncertainty. But we just don't know when or how fast it will converge. So that's pretty annoying. And there's also the issue with low-rank models or tensor models is that every sample, if you have 1,000 samples, then the first sample and the last sample, the ordering of the components might have switched, or it might be different components entirely. So that's a little bit of hassle there that can be annoying in practice. Variational Bayesian inference, which is what I mostly use, is that we do a functional approximation of this. So we try to say, can we approximate, not of the posterior, of a P of X. So can we do an approximation of that? So we have our true posterior, or we have our true posterior distribution, and we have our approximating distributions. So it's called the P distributions and the Q distributions. It's not important, but that's kind of just the custom to do it that way. And then you can lower bound this log of the evidence, and then you can get what is called the evidence lower bound, and then that has a nice form that you can optimize in and derive updates rule from. But it is an approximation, so it's very nice if you go from never having applied Bayesian optimization, or never having done Bayesian inference at all. If you then go to now, how should I actually work with Bayesian inference? So it gives a very ALS-like approach as well. Convergence, it's easy to access because you have the same guarantee as in ALS. Or in ALS, you have in maximum likelihood-based alternating least squares, you have this guarantee that each step will always lower the error. So you know that it will converge, and you can monitor the relative change in error, and then say when that is small enough, you have converged. You can do the same thing for variational Bayesian inference, but there you measure the change in this evidence lower bound. But otherwise, it's exactly the same to assess convergence. And both of them have the issue that you're not guaranteed this true posterior distribution or the true parameters. They have a lot of you can only get a local minima, or you might risk getting a local minima and not the global optima. it's easily interpretable, because even though you get like a approximation of the distribution, you have the mean of the distribution and the variance of the distribution. So you can quite easily just take the mean and then use that as you would have the point estimates of a maximum likelihood distribution, or a maximum likelihood estimation. So this all sounds very complicated, so I thought let me give you a small example of just taking a CPD model and then seeing how do we fit it. And here I could have made it even simpler and not having it do n factor, but this is the model for CPD. This is the data. If we do least squares, we are interested in how do we update the factors and how do we measure the error. So the factors becomes, there should be an explanation of what B is. Let's see, there it is. Yeah. So for one factor, the A of n, we kind of condition of all other n's that's given by this index here, everything that's not n, and then we update it. So we have this second order term here, and then we have our data multiplied by our factor, or our data matrixized multiplied by the other factors. And you can kind of see that, or this here is called the matrixized tensor times Chatry-Rao product for the CPD. And that is basically, the matrixized data multiplied by all other factor matrices given by this one here. And then we have to account for the scaling and the cross correlation, and that's done by calculating this term, which can also be calculated efficiently. So we can kind of update the factors one at a time, and then we can model the error. Here it's written as kind of the vectorized version and the vectorized version of the model. In Bayesian CP, we have to specify these prior distributions, and if we do variational inference, we have to specify these Q distributions, and if we do empty sampling, then we get some distributions out, and these distributions turns out to be the same for what is called block dip sampling. It's not so important, but it's kind of, you get this as a kind of an approximation. Now you have to update this. So we want to update mu for a specific mode n. We condition on all other modes similar to the least squares CP, and then we want to find the mean and the variance. And that has a very simple form in that we have the same product here as over here. We have this tau from the likelihood function that now comes into play, and then we have this identity matrix that comes from the prior. And in practice, you would either scale your data so that this is not a strong assumption, or you would add like a scalar value that you multiply to. So if you have that this becomes 0, then everything starts to look like the least squares update. Okay, but that's the second moment. And then to find the mean, we take the inverse of this, and then we multiply again by the matrixized, or we calculate this matrixized tensor Chatry-Rao product. And then these kind of brackets here are because if we do variational inference, we have to get the expectation of this. And that actually turns out that you can do that very simple. Or it depends on your assumptions in how you build your Bayesian inference, but mostly we do simple assumptions, and then we get the exact same relation here, and this expectation becomes the expectation of each of these things on its own. So it doesn't become too complicated. And similar for this one here, the expectation just moves into each factor. So if you do variational Bayesian updates, after having updated the distributions, then you can kind of say our estimate of the factor matrix is just the mean value. So it's kind of like a point estimate, or you can use it that way, but it has built in the uncertainties and all the other nice things about Bayesian statistics. And then sometimes you need the expected second order moment, and this is also a standard form. Now, if you do empty sampling, instead of using the mean of the distribution and the variance, you draw a sample from the distribution, and then you treat this sample just as kind of, then you have none of these brackets. You just use the sample that you have, and up until now, nothing really has been gained by using Bayesian inference. So I will say one of the things I find most nice in Bayesian inference, and that works. It doesn't always work, but it works most of the time, and it generally improves kind of the solutions, is to simply change this prior to what is called an automatic relevance determination prior. So we change our prior on A to say, well, there should be some diagonal precision that we can tune. So we have to learn this lambda. And then we simply get this update here. So it's a very small change to the update. It's only really as the identity becomes a diagonal matrix, and otherwise everything is the same. So simple change that is very powerful, and I will show why later with some results. Then you might ask, what about tau and lambda? And this also looks a little bit complex, but tau, you can either fix it beforehand, and that's if you have a good estimate for what the noise should be. But you could also update it, and that is just specifying what's called a gamma distribution on your prior, and then the Q distribution becomes, or your approximation distribution is the same, but now you have to estimate this alpha tilde and beta tilde. And it's really simple. It's kind of the size, or it's how many elements you have in your data, plus whatever you have for value in your prior here. And then beta is, your prior plus basically your least squares loss, right? This is the exact same as the least squares loss. So we can kind of see this one here, the vectorized data, the vectorized model. It's the exact same. And then you just update by dividing those two by each other. The automatic relevance determination, very simple as well. We can do gamma priors for this noise precision, and then we update them where they are the sum of how many observations there are in each mode. And then to get beta, we have to get the second order moment for each factor. So also something we have already. And then updating is simply dividing these two by each other. So it's, so maybe a final comment there is that computationally, this doesn't add any kind of significant cost. There's nothing, these are all things we either already have calculated or that are very quick to calculate. So more generally, Bayesian tensor decomposition, we take some likelihood. I have only worked with the normal likelihood because that's usually the most relevant for us, and it's the most, it's the easiest one to do. So you have, your data X, vectorized data X, vectorized model M, you have a tau, and then it's basically trying to fit that. And then we have, Tucker, CP, tensor train, block term, decomposition. And then you have to specify these prior distributions, and usually it's pretty clear what kind of distributions you're choosing. It's the same as considering constraints. Like maybe you want your vectors to be non-negative, or maybe you want them to be real valued or non-negative, or you say I don't care about what they are, but they should be in some specific interval. They might have to be orthogonal. Is also a very used assumption, and then you can specify these component scaling, or these automatic relevance determination. And then you could do noise modeling. So I talked about a single tau before, but you can also do a tau on each mode and each observation in that mode. So to kind of start with an easy example is to just take a non-negative matrix factorization, or MCR. This here jumped up. Okay. But basically here we specify automatic relevance determination of each of our components, and then we investigate kind of should we model our W and H as okay, there's a lot. No, okay, no, that's fine. So we check different priorities. Should it be truncated normal distribution or should it be an exponential distribution? Because we are interested in non-negativity, and both of these give non-negativity. And exponential distribution is kind of similar to doing an L1 norm penalization on your parameters, and truncated normal is similar to doing a L2 norm. And then we have our noise precision, and then here we have our data point K, which we can kind of say, well, it comes from some W matrix, some H of K vector, and tau, and then we have this likelihood here. And we contrasted it to, so it's maybe different performance of the probabilistic NMF with if you do just maximum likelihood based NMF, or you do maximum likelihood based as an NMF where you try to where you fix the sparsity level. So you say each factor should have 5% sparsity or 30%, depending on what you set it to. Or you do kind of a more soft penalization. So you can say this is a hard penalized sparsity and this is a soft penalized sparsity. And if you look at just the NMF solution, so this here is a synthetic data set called the swimmer data set. So basically a swimmer has a torso and 4 limbs, and each of these 4 limbs can have 4 different positions. And then your data is basically all the possible combinations. And there's, I think it's 264 combinations. So if we do NMF, we can see that it splits the components out. Like it tries to use all the components, and it doesn't really look nice. We can kind of enforce sparsity, like a hard sparsity, but there's no really good solution where it splits the data in any of these. We can do this more soft sparsity, and there we see something that's nice in that we get the torso as 1, and then the legs coupled to the torso, and then we get mostly we get limbs on the others. There's also some weirdness, and there are some things that I have no idea what happens here, for instance, right? There's some weirdness that you can increase the sparsity constraint or a positive sparsity penalization, and then in the end you get something that actually looks nice, that you get a torso on its own, and then you get almost looks nice, right? Because you still have 2 limbs here that are not really ideal. If you do a probabilistic NMF either with the truncated normal or the exponential, you kind of see 2 possible solution spaces. So now every limb has its own component as it should, and we don't have we have a lot of 0 components because there's no reason to use those. And then the difference between these are basically that the exponential prior favors sparsity, so it places the torso with a single limb, whereas the truncated normal doesn't favor sparsity, and then it places the torso on every limb, but at 1/4 the intensity. So when you sum these up, you get a full torso. So it really solves this problem. You can do something similar on MNIST, where you can kind of see that you can do NMF, you can do sparsity constraints. There's no really it just eats as many components as it's given. And then if you do the Bayesian NMF or probabilistic NMF with automatic relevance determination, you automatically kind of reduce the model space. So this is very nice. These, of course, are not very analytical chemistry-wise. So, of course, there should be a data set. So most people working with tensors will have seen this solution. So I didn't plot the data set, sadly, but it's a 3-way fluorescence spectroscopy for emission excitation matrices. And it has 3 components, and you can kind of see how they look here. And this is a model that fitted with 10 components, and then just learns that you should only use 3 components. And here, just kind of to showcase case what heteroscedastic noise means. Here we put like a rank 1 factorization or rank 1 approximation of the full noise matrix. So we get a vector or we get a noise precision for every sample and for every emission wavelength and for every excitation wavelength. So you can kind of see that there are some areas that are more noisy than others, and some samples that are more noisy than others. And let's see. Yeah, so this here is just that it's nice that it still prunes the components down, and we can even specify, more components that it will still prune it. This probabilistic perfect 2 is another method we've worked with, and here I included this because it really shows what we kind of always see. So we like to plot this SNR versus fit plot. So the SNR is the signal to noise ratio. So at 0, it means there's equal amounts of signal and noise, and above 0, there's more signal than noise, and below there's more noise than signal. And if you increase your dB by 3, then you increase the signal by 3. Or if you decrease it by 3, you decrease the signal by a factor of 3. I'll correct. If you increase the signal by 3 dB, you double the signal. And if you decrease it by 3 dB, you halve the signal. Just kind of as an intuition. And then this here is, well, it says notchless fist, but it's basically kind of the ground truth. Can we recover the ground truth? And in our work with probabilistic perfect 2, we investigated 2 formulations of this. Like I crossed this one out because of the 2, you should always use this one with Mrs. Fisher matrix distributions for enforcing orthogonality of the factors. Okay, so in the left plot here, we take the direct fit model, so that's the maximum likelihood-based model developed by Rasmus and Kiers, I think. And here we say we know the true number of components, which is 4, and then we fit it all these places. So we can see if there's enough signal, everything kind of performs similarly, and then as you add more and more noise, the red curve becomes slightly better than the direct fit, but not by much because we know the right order. If you then don't know the right order, so if you just kind of increase the number of components by 2, then we can really see that's a problem for the direct fit model because it doesn't have this automatic relevance determination and it doesn't have anything that says you should reduce the number of components. So there we really get like a nice increase in how well our method performs when the signal starts becoming lower and lower. If we have enough signal, it doesn't matter. Everything is kind of the same. There's no uncertainty if you have perfect data. So if you then also change the noise assumption, which is not exactly fair because the direct fit model has a homoscedastic noise assumption, but then you can kind of see if you have the correct model order, they're still kind of good, but as soon as you hit lower noise levels or higher noise levels, you really see that you should model this noise. And if you then both have the wrong noise model and you have the wrong component order, then you really see a big difference. And I don't know if we're always in the case of heteroscedastic noise, but we're definitely always in the case for what I'm working with, in that we don't know the model order in advance. So this is super nice. I think in the interest of time, I will skip this, but it's basically just doing non-negative CP on some brain imaging. And the main takeaway here is that in our results, we kind of tested various Bayesian inference versus Gibbs sampling for recovering missing data, and in particularly missing fibers here, because that's actually the proper missing mechanism for this data. And at least from what we've seen, we recover our test data better using a variational Bayes than our get sampling. If this is true in general or not, that's less unclear, but at least that's kind of where our results have shown us to look. So that's also a reason we use VB a lot. This here is, so Basmus, how much time would you say is left?
Go ahead. We're
Okay.
good. We're good.
So here we have the EEG data, which is brain imaging data, where you have electrodes placed on a scalp that you measure, and then you have multiple subjects going through some experiments. So you have them going through several trials of the same experiment. What you would really like to understand is how does this differ across subjects and trials. So if you just do maximum likelihood CP, it is three-way data, then you get something that looks very similar, and that's not so nice. So what people have done in literature is to say, well, we enforce orthogonality, and then you get brain regions that are kind of, here there's a clear difference between front and back, and the second component measures something else as well. There's some clear distinguishing between what it's doing. But orthogonality is not really what you expect the latent signals to be in the brain. You don't expect that they'll be uncorrelated to each other. So we investigated this with the Bayesian CP with heteroscedastic noise. So we get these nice kind of front and back regions here. The time activation has to be on top of each other, because this is kind of, the dotted line is where something happens, and then kind of the first 400 milliseconds, which is roughly here, is where we expect to be seeing most of the signal. And then you can see how it activates across different trials. And then we have this noise estimation. So you can also see that here there's very little noise, because that's actually where the data kind of been standardized and moved to. And then initially it's fine, but then you get more noise, because this is really the dynamic region. And then out here, it doesn't matter, because then it's just noise as well. So and you get also this nice noise map saying, well, there's more happening in the behind, or in the back of the head, which is where the visual cortex is, and this is a visual stimulation task. And then you also get noise-specific variances. So you get something that's interesting, at least. We also looked at, so one of the things that kind of we really want to use probabilistic tensor decomposition for is model selection and model order selection. So model order selection is really kind of this automatic relevance determination. Can we prune to the right model structure? And model selection is more, if we have multiple models, can we then say which one is the best? So we showed this for a block term decomposition, that if we have a true block term decomposition model, so this is kind of ways of writing a block term decomposition model. It doesn't matter so much now, but basically you want the diagonal to be bold here. So we use this evidence lower bound that we get from variational Bayes, where higher is better. And then we also have the relative reconstruction error on the noiseless data. So that is how well do we recover the ground truth. So ideally, both of these should kind of be the bold curve. And we actually see that mostly kind of point to the right model. Here, it turns out that this one is actually slightly better, but mostly we point to the right model with its elbow, and it in general also points to the same model with the relative reconstruction error. So it's important to kind of note that the bottom part here of a plot of the table we would not have for real data. For real data, we will always have this top part, but we don't have the bottom part. This is kind of similar to the perfect experimentation, is that in that we have a signal to noise ratio here, and we're trying to recover the ground truth. And then if we know the true structure of the model, this probabilistic tensor decomposition or block term decomposition is not really like, they all perform on pair. And if we then have too many components, so rather than having the true structure of 333, we now use 666. And then we see immediately that kind of there's still like the variance in the data grow, but it's still it's still significantly better than mean here. And then just for everywhere it's by reviewers, so it was nice to kind of look in that if you take like a simpler structure, this structure here, it's known that you will have unique solutions under some relatively mild conditions. And if you do that, you can kind of see that all the models perform pretty well. What is interesting in terms of speed is that of these two maximum likelihood-based solutions, the black one is, or this one, the orange one is the fastest. BTD or probabilistic, the probabilistic version is twice, or is not twice as fast. It takes twice the amount of time, but then the best one of the maximum likelihood approaches takes 20 times more than the BTD. So you actually do get something on the speed as well. This is something on shift NMF, which we have in Bayesian shift NMF. This is something we're preparing now, and I think I'll just skip to what is kind of the nice results is in that we look at this for NMR data. So I've been looking a lot at nuclear magnetic resonance data, and then you get a plot like this, like a small section of the data, and you are asked kind of how many peaks are in this data. So there are 3,000 samples here, so there are 3,000 lines. And if you use NMF, it's the wrong model, right? You don't have the data, you have these couple of peaks that kind of shift back and forth. And basically, NMF is the wrong model. If you add ARD to it, it's still the wrong model. If you then say, I align my data, so you try to kind of try to pick a reference sample, and then you align everything towards that reference sample, then you still get the wrong model because there's more than one shift in the data. And then you can do this multiple shift that we will kind of present. So there's something called shift NMF, so we can already look up what that does. But we can actually see that we, more or less perfectly describe the data. Of course, there's some residual noise, but nothing kind of significant. And then we get some really nice components out. And that's kind of with the R squared here. It's almost 1, and then we lose a little bit of explainability to go to 3 components here by the blue curve, but we still have, I think it's 98% of the variance or something like that. So it's very nice that we can kind of automatically learn that this is the way where the place we should be. Okay, so most of the work I've presented here is mainly by me and co-authors, but there are of course other people doing probabilistic tensors, and that's really covered in the papers as well. There's this toolbox that you should check out. It includes CPD, Tucker, TT, and BTD, and I think the prints or the benefits are that you can kind of, I will actually show all the benefits here. Let's see. The benefits are really that you can kind of recruit information in a very structured and principled way through these prior distributions. You get this penalization of model complexity, so that means that we favor models that are simple, and that's often a good assumption when you work with the chemical or physical data. We have nice prediction of missing values. We have improved noise estimation for heteroscedastic noise. There are also some additional techniques for how to compare and select models in the Bayesian setting. And there are also good ways of predicting or principled ways of predicting on held out slices of the data or subtensors based on on this conditioning of random variables that is done in Bayesian inference. I thought I got a double. You also get this stereo distribution and the uncertainty quantifications. And then depending on whether you do variational Bayes or Gibbs sampling, you get different quantification. You get a different degree of the reliability of your quantifications, uncertainty quantifications. So overall, these are some of my takeaways working with Bayesian tensor decomposition, is that it's generally as good or better than maximum likelihood, and it's really beneficial if you have few samples or complex models or many interactions, or you just have a lot of noise in your measurements. The automatic relevance estimation doesn't always turn everything off. You really need your model to match your data, but still it gives robustness to if you specify too many parameters. You don't have this issue of degeneracy at all that you have in maximum likelihood based models. I think I've said what I wanted to say about Gibbs and the VB sampling already. Both are fine choices. And then Bayesian inference can be implemented as efficiently as alternating least squares. So I think sometimes people hear Bayesian inference and they say, oh, it's too slow, and that's true maybe 20 years ago, but not today. The test through stochastic noise modeling is quite interesting, but you really need there to be noise. If there's little noise, then you cannot, it doesn't matter that you model the true noise distribution. If the true noise is close to zero, it doesn't matter. In practice, when I look at these things, I found that the best thing before doing Bayesian tensor decomposition is actually to think about what is it even that you want to do. What is the baseline method you're comparing against? How do you even compare results, especially since a lot of tensor decomposition problems relate to things where we don't know the ground truth. So how do you compare that? When you start to consider how should I model my data, then think about how much signal is there, where's the noise, the model you're using, is that actually something that's nice, or is it just a bad model for your data? And also, do you want to get these uncertainty quantifications? So Bayesian inference is nice, even if you don't need the uncertainty quantifications. They're built into the estimation, and they remove some spurious local optimus, is my intuition about it. And then for actually doing Bayesian tensor decomposition, you want to set up these hyperpriors in a nice way. There's some literature on that. So you're basically modeling the automatic relevance determination by specifying a gamma distribution with some prior parameters. And usually I set these to E2 or 10 to the power of -4. But if you don't standardize your data to norm 1, then you should account for this in how you standardize them. Usually I like to do random initializations, lots of random initializations, and then find the best one. But if you want it to really be for speed, it's probably better to initialize in a maximum likelihood estimation or a maximum likelihood estimation solution, or another unfolded solution that you then tensorize in a way. It's also important that you gradually start fitting through you should initially just fit your model factors and core array, and then you can open up for the automatic relevance determination, and then you can open more up for noise estimation, because otherwise you can get some funky effects. And here n is maybe 10 or 50, and similarly for m, so it's not huge. I think, this is it. Thank you for listening. The toolbox is online, and you can see these links if you want to follow my research or ask me questions.
Excellent. Thank you so much.